It's actually my pleasure to introduce our special guest this evening. Dr. Miguel Nicolelis is the Duke School of Medicine Professor of Neurosciences, Professor of Neurobiology, Biomedical Engineering, and Psychology and Neuroscience. And he's also the founder of Duke Center for Neuroengineering. He's a native of Brazil, where he received his MD and PhD in neurophysiology from the University of Sao Paulo. While Dr. Nicolelis is perhaps best known for his achievements in developing brain-machine interfaces, which are also known as BMI, and his neuroprosthetics in human patients and non-human primates, monkeys primarily. He's also developed an integrative approach to studying neurological and other psychiatric disorders, including Parkinson's disease, epilepsy, schizophrenia, and ADD. Neuroscience laboratories around the world, including the US, Europe, Asia, Latin America, have all incorporated Dr. Nicolelis' multidisciplinary approach to studying a variety of mammalian neurosystems. And his work has greatly influenced both basic and applied research in computer science, robotics, and biomedical engineering. Dr. Nicolelis is a member of the French and Brazilian Academy of Sciences. He's authored nearly 200 manuscripts, edited numerous books in special journal publications, and he holds 3 US patents. His award-winning research has been published in Nature, Science, Scientific American, and has been reported in Newsweek, Time, Discover, and numerous other TV networks and media outlets. Perhaps equally important for the students here tonight, his 2011 appearance on The Daily Show with Jon Stewart actually opened up a generation's eyes to the fact that neurology could actually be cool. But his TED Talk, which he gave last year and is available online free at TED.org, is an absolute must-see. It's fascinating. And we're blessed to have him here tonight to share more of his thoughts and his research with us. So with no further ado, I'm here to present Dr. Miguel Nicolelis.
Thank you. Thank you very much. Thank you. Thank you very much. It's a great pleasure to be here. Good evening to everybody. First of all, of course, I'd like to thank the organizers and the sponsors of the STEM Summit. This is the kind of initiative that we have to have all over the country, in fact, all over the world. I think this is the passport to a better humanity, a better planet, and to enhance education and to enhance the opportunities for young kids to fulfill and to pursue their intellectual dreams is perhaps the greatest mission that we, the elderly, can provide to the next generation. So it's a great, I'm very moved and very happy to be able to talk to you about, as Dr. Hunter referred to, this new kind of brain research. And I like to, when I start these talks, to first to put you at ease, to say that if a Brazilian can talk about brain research, you're fine. So don't worry. And it's not rocket science. It can be understood, you know. So, but the first thing I want to give to you is a perspective. Why brain research? Why it matters to understand how the brain works. And the simplest and most relevant thing I can tell you about it, or the reason, the rationale for it, is that to understand what exists between our ears is to understand everything that deals with human nature. Our history, our art, our poetry, our desires, our passions, our past, our present, and our future, the entire concept of the universe that you have, and we share and cherish, comes from here. Comes from this universe that we have between our ears, that is as complex and as humongous as the universe that we can see on top of our heads. If you doubt that, I can give you just one number that will settle the issue. There are as many neurons in your head as there are galaxies in the universe, about 100 billion. And it's this universe that tells the story of that one. Okay? There would be no story of the cosmos if there was no conscious mind to create a model of it and to report it in all sorts of languages, you know? So what I want to first show to you how we do this thing, how do we do brain talk, you know, brain shop talk, as my students tell me. I want to introduce you to a concept that you all talk about, but you never probably saw or heard, and that's the brainstorm. Everything that we do everything that every single human being has ever done or will do, as long as we are the same species, comes from this kind of brainstorm. Because everything we do comes from microelectrical storms that crisscross our brains and produce everything that is out there. And I'd like to show you, if you can see, I hope you can see with the light, the first time that we ever recorded a real brainstorm, not the kind of thing that we talk that we are going to do every morning. Oh, I'm going to do a brainstorm. My kids tell me that all the time. And one day I took my kids to the lab to see this. This was the beginning of this new neuroscience. It's about 12 years ago when for the first time we could record. We spent almost 70 years recording one cell at a time. And what I mean is recording the electrical pulses that one cell produces. But there are 100 billion. How could you understand this thing looking one cell at a time? It's almost trying to go to the rainforest in the Amazon, in the South American Amazon, and trying to understand that ecosystem one tree at a time. It'll take a long time. And you're never going to get there. So 25 years ago, when I first came to the United States, my advisor and I decided that we wanted to hear brainstorms and listen and report and quantify them, not one at a time, but in a large number of cells at a time. So what you're seeing here is the first image ever published of 100 neurons firing over time. This is a brainstorm. What you see is a thought, a snippet of a monkey thought that is trying to understand what a visual cue that I'm projecting on a computer screen means in terms of where he has to move, given this cue. It's more or less like what we all do in Brazil at 18 here a little earlier, when people come out of nothing and tell us, you know, to drive this beautiful car that your dad is giving to you, you're going to learn this simple rule. And in São Paulo, Brazil, where I come from, the rule is like this. If it's red, you stop. They're from São Paulo, I can see it. Yeah. They left before I said it. Well, if it's red, they tell you stop. If it's green, go. And if it's yellow, you speed it up, cross the traffic light, and don't get a ticket as quickly as you can. Well, this is the same kind of cue that I was giving to these monkeys, and they were learning to move their arms according to the color of the light I was flashing in the screen. And the question was, could I look at the brainstorm and predict ahead of time, half a second ahead of time, what these monkeys are going to do? Could I read this thinking and say what these monkeys are going to decide about this light and how they're going to move their arms? That was the question that got us going almost 3 decades ago. Well, I showed you briefly a brainstorm. I'm going to let you hear, as my kids heard in the lab, what a brainstorm sounds like when you're recording these 100 neurons, throwing these in loudspeakers. You're in a little room and these loudspeakers are playing a brainstorm around you. It's not quite the same experience in a theater, but it's close. And that's what my youngest son heard, Daniel. That's 100 cells firing. According to Daniel, that sounded like listening to a badly tuned AM station while making popcorn on a microwave. 35 million years of evolution, and you're doing popcorn in your laboratory. So we could listen to that. We could measure for the first time these signals, but the question is, what could we do with them in real time? There were many theories. For 100 years, we had theories on how the brain actually does that. And as you know, scientific theories are like football games. You know, you have fans on one side, fans on the other side, and a mess in between, right? Trying to decide who is right. But there was no paradigm to decide some of these theories. So that's when John Chapin, actually he was here in Dallas when he was a graduate student at UT Southwest. And he moved to Philadelphia and we hooked up. And in the late 80s, we started developing a technique that for the first time allowed us to record lots of cells at the same time, simultaneously, lots of these popcorn firing neurons. And it occurred to us that even though we could show what I just showed to you, the images and sounds, we needed to measure and we needed to see, to test these theories, whether we could produce behavior out of these storms as the brain does with our bodies. And that's how we come up with this preparation that became known as brain-machine interface. We published this in 1999, and for the students here that one day will be scientists, or businessmen or engineers, I just want to give you a little quick life lesson. We sent this paper in, it was published in Nature, we sent a big grant to NIH, National Institute of Health, and the answer we got in 1999 from the reviewers was Dr. Nicolelis and Chapin need help, comma, professional help, quickly. They're going crazy. They want to link brains and machines. This is 99. 2011, feed forward 2010, I'm sorry. This field won the most prestigious NIH award. We won the Pioneer Award by NIH, not from the same reviewer, I have to say. But when I got the award, I went up there with the director of NIH and I said, if the reviewer of that grant is in the audience, I have just good news for you. You're wrong. Right? So basically, what we did was, since we got a technology I'm going to show you very quickly, and I want to show the technology because I want you to realize that brain research is not anymore what you thought. It's not only just a medical discipline anymore. It's perhaps the fastest growing multidisciplinary research field of our time. Because in my lab I have engineers, mathematicians, physicists, mechanical engineers, electrical engineers, nanotechnologists, working together with physicians, neurosurgeons, neuroscientists to do this stuff I'm going to show to you. It's a completely different ballgame. So what we decided to do to test these theories was, first, we designed this technology that allows us to record brainstorms, but we're not happy with that. We wanted to transform these signals that you just saw into digital signals and try to extract in real time from these digital signals the motor commands that the brain is creating to move the body. We wanted to take them out, transform them in digital information, and send to machines that could actually enact the voluntary will of those brains in parallel with the body. And as you're going to see, in a given moment, replace the body. Because the animals realized that they could do this faster just by imagining what they wanted to do and let this piece of machinery enact the motor behavior that they wanted to create. So in doing so, John and I wanted to test a particular theory. This was created to test a very abstract theory that I'm going to mention to you in a moment, but we realized very soon after that the moment we create a brain-machine interface and we're able to, in addition, to move these devices just with electrical brainstorms, to send feedback signals back to the animal's brain or to the patient's brain so the subjects could actually realize very quickly what these devices were doing in real time. We create a completely different way to interact with the brain, in a way to test these theories that could have ramifications much bigger than just solving a bloody academic fight. We started to think, and there are many, and they are very puny most of the time, but we made a lot of them, but in reality, we realized that this could have a profound influence initially in medical rehabilitation for people who cannot move anymore because of a lesion, let's say, of the spinal cord that doesn't allow these brainstorms to go all the way down to the body and generate the motor behaviors. So I'm going to get at the end to this part to see how when you invest massively, as this country has done throughout the century, the past century, in basic science, not even knowing what is going to come out, something will come out, and something big will come out that you cannot predict. But it doesn't matter. You need to just be there at the right moment to harvest what you get when you invest in high-quality science. So let me show you how a brain-machine interface operates. And in a couple of experiments, you understand immediately the power of what this can do for us, not only in medical rehabilitation, but also in the future of our interfaces with computers and eventually the way we communicate. So this is just to show the kind of sensors that we use to record brainstorms. I have been doing that for 35 years now. We're in the 4th generation of this stuff. And these are electrodes that we implant about a couple millimeters inside the brain of these animals. And we actually can get, right now, I didn't tell you the full story. When I came here in '89, the biggest ambition that John Chapin and I had was to record 20 neurons in 5 years. We did. We actually recorded 50. We published a paper in Science, this was 95. Today, we are recording 2,000. And in 5 years from now, you're probably going to hear that a lab, ours I hope, recorded 50,000 simultaneously with this technology. That involves a variety of things, but what you see here is the same brainstorm that I showed you before. Instead of 100 that we had 10 years ago, it's 2,000 neurons now. And as you're going to see in a moment, that makes a big difference. This jump makes a big difference. This is how these implants look like. They can be encased in the bone. They look like a heart pacemaker. In the future, you're going to have people walking the streets, as you're going to see in a moment, with a robotic vest, people that are paralyzed because of a spinal cord injury, a car accident, a football injury, or a diving injury, very common. But you're not going to see wheelchairs anymore. I hope in my lifetime that we are going to see this. We are going to see people walking upright, controlling a robotic vest with brain signals coming through this vest and enacting their locomotion by voluntary will as if that body was theirs. And that's what I want to show to you, how we got there, how we're about to get there. I like to call this the neuroscience moon landing. I'm from the 60s, so I became a scientist seeing the Apollo program unfolding. I had no idea about the political implications of that. I couldn't care less. I just wanted to see those guys landing on the moon. And neuroscience is about to do a moon landing of, equal proportions, in my humble opinion, because there are about 45 million people in the world that cannot move because of a variety of disorders. And if this can work, and some people can restore their mobility, it's going to be equivalent to a moon landing for each one of those people that today cannot do that single gesture of stepping on the ground or unknown ground. So let me show you how this works. This is our first very famous monkey, now very famous now, 10 years later, but this was in 2002. This is a monkey that was learning to play a video game like we play video games, and monkeys love to play video games like us because they get a reward. Every time they get the game right, they get a drop of juice, particularly in our lab, Brazilian orange juice. And a monkey will do anything for you for a drop of Brazilian orange juice. If you can train that at home. You can try that at home. It will work, I guarantee it. So these monkeys, they learn to do this playing of this game. That is a very simple game, but it's very precise, as you're going to see. They're using a joystick. Aurora is using the left hand to move this joystick to put that cursor, computer cursor, inside a target that appears in random locations in the screen, 32 different locations. As a good primate, she's trying to cheat. She's trying to guess before, and sometimes she gets it. But crime does not pay because it's impossible to cheat to 32 different locations. So she has to concentrate, and when the target appears, she stops the cheating and tries to make a beautiful trajectory inside the target. Well, at that time, this is in Durham, that's the winter of 2002, and we are recording here. You can see the cables here. Today is all wireless, but at that time we had cables coming out of these implants, and we had 100 neurons, the first brainstorm that you saw, being recorded in real time, and our computers, using a particular type of mathematical model that we developed, were extracting in real time the motor information out of that brainstorm and trying to make a robot that was in a different room reproduce the hand movements that you just saw Aurora do. Because the idea was, after a month, to turn on this brain-machine interface and let Aurora realize that there was no point anymore in using her own body to play the game. She could now just imagine the trajectories because our brain-machine interface would decode the motor thinking that she had and would basically make a robotic device reproduce the trajectories that she had to do to play the game and get the juice. Because the bottom line here is a little bit different from our society, but the bottom line here is orange juice. Get the juice, right? So what you're going to see, the next movie, is the first moment in which a brain liberated itself from the physical constraints of its body and were able to act in the world just by thinking, because there was a piece of machinery capable of enacting its voluntary will. And that's what Aurora did. This is 5 minutes after that video. Notice that the joystick is gone, because Aurora has relaxed now. The brain machine is on. We are recording the brain activity and sending to a robot that I'm going to show you in the next video clip. But all the trajectories that you see at the cursor now are generated directly from the brain activity coming out of Aurora's brain. Even the cheating is there, right? But she continues to play the game. And that was a shock for us. There were 3 people in this room, a Brazilian, a Spaniard, and a Russian. And none could speak, what is a miracle, right? A Russian, a Spaniard, and Brazilian, not speaking. For an hour, we followed this lady playing this game without moving a muscle. And she was getting all the juice she wanted. Which is, again, for my Brazilian countrymen there, a Brazilian dream. A free lunch with no work whatsoever, right? So, the reason Aurora could do that, we realized a month later, this is 30 days later, is because she, by all purposes and means, had acquired a new arm. Not her, but her brain had assimilated this robotic arm as if this arm was an extension of Aurora's body. And he was capable now, the brain, I mean, to control the 3 arms simultaneously, the 2 biological and the robotic one. There was no loss of biological function, and yet, you see, she can move the arms, but she can continue to play the game with the robotic arm controlled by her brain activity alone. And some of you may be wondering, there are 100 billion neurons in her head. We are recording 100. That's a tiny fraction of the total. How on earth can that work? That is the biggest mystery of all this research. And it changed, in my opinion, the way we have to look at the brain. Because it suggested to us that the theory that we're trying to test was right. A theory proposed in the late 40s by a guy who nobody paid attention to for a long time, a Canadian psychologist called Donald Hebb, that suggested that the brain actually works as a voting device. Every neuron carries a little bit of information, but you need voting of lots of neurons to get this thing working, but you don't need billions to get a behavior going. You need a much smaller number because the brain is actually looking on a draw. It's making a draw at every moment in time. Out of these 100 billion, it's getting a couple thousand to do something here, something there, and is drawing from the pool of potential players or voters the actual universe that will do the job that you need to get done. That's very different from what, the theory that we know in textbooks that is out there, is still in medical textbooks. So feed forward 10 years, lots of different technologies have changed. In fact, our electrodes have become smaller, higher density, and now it's all wireless. Instead of 100, it's 2,000. In this particular case, 500 neurons being used. And now, our new monkey, Cherry, can play the same game without any cables, without sitting anywhere. She actually lives in an environment where everything that she does is controlled by her head, by her brain directly. She's playing Aurora's game at much higher efficiency, and she actually is doing this quicker than she would do if she were trying to use her own hand to do the task. And she's drinking juice like a mad monkey, as you can see, right? So the first case that I showed to you is just a cursor. And my friends in the neuroscience community in 2000, probably their reviewer of NIH, the same guy, came and said, oh, this is just a cursor. I said, well, just wait. So this is the same monkey that you just saw, Cherry, and she started to learn with the cursor, but now she can control a cart in our lab. She actually drives a cart in the lab, and it's like the lower part of an electronic wheelchair. She can be one part of the campus, in the East Campus at Duke, and the cart can be in the West Campus, and she can do that over the internet and control it. In fact, I'm going to show you in the next experiment a monkey that was at the East Coast of the United States at Duke University controlling the walking of a robot in Kyoto, Japan in real time using the same concept. So once you liberate this thing out of the head, lots of things are possible, So this is the last incarnation of our experiments, and I'm going to show a few demonstrations so you understand what is possible today. This is now, robots are very expensive and, extremely expensive. You can easily spend tens of millions of dollars building a humanoid robot. We decided to use the cheaper version, and this is a monkey avatar. is a realistic monkey body that is programmed with all the kinematics and all the real descriptions of a monkey body, so we actually can control this body using brain activity generated from our animals. So this is a study that we just finished. It's not even published, but it's the first time that a monkey was able to use both hemispheres, as I showed you in Aurora and Cherry, to control both arms of this avatar and to perform bimanual tasks. And in this case, where the figures appear, the monkey has to bring the arms inside the solids in a virtual space. So the monkey is watching the world through the eyes of a virtual body. In fact, what the monkey sees is like this. It's like, it has these arms in the virtual space and is basically trying to put both hands and arms in a position so that the fingers touch the inside of the objects. It's a very difficult task. If you try to do this with 2 joysticks, it requires training for any of us to actually do this. The monkeys are doing this just by thinking. They're not moving their bodies at all. So they learn this in about 30 days, and they can do that, after that continuously. So what do we notice? This is just a little bit of mathematics I'm not even going to talk about. It's just to show you that the whole game here, in terms of accuracy and what you can do in terms of motor behaviors with these brain-machine interfaces, depends on the number of neurons that you record simultaneously. And that's the reason I said that it's so important to increase this number in the next few years. We actually have calculated how many neurons will be needed to control a whole body exoskeleton, a robotic vest that a quadriplegic patient, a patient that cannot move below the level of the neck, would be wearing. How many neurons would be needed to actually control this vest so this patient can imagine walking or moving both arms and do it just by thinking? And believe it or not, this number is not billions. It's in the order of 50 to 100,000 neurons simultaneously. That would take someone out of bed walking the streets. It's about 1.5 orders of magnitude of what we can do now. In my career, in my 25-year career here in the United States, I went from 20 to 2,000. So I went 1 order of magnitude, 200, 2 orders of magnitude. I'm 52. So I still can get to the point where we will see 100,000 neurons recorded simultaneously. I truly believe in this. And if that happens, things like this start becoming possible. That's the experiment I just mentioned to you. So I have to just make a little parenthesis here. It's very dangerous to put a Brazilian and an Australian in the same room, particularly if they're scientists, because they come up with experiments that are a little different. So one day I met Gordon Chang, who is the greatest roboticist alive. And this is a guy who is born in Macau from a Chinese family who grew up in Australia, so he considered himself an Australian, and used to live in Kyoto, Japan. So he speaks 8 languages, and his robots speak many languages. That's the interesting part. So Gordon was the first one, together with an American company, to build a humanoid robot that is a piece of art. This guy is called CBU1, computational brain number 1, and he has everything needed to be an autonomous robot, but one thing, a brain. They couldn't come up with a brain because nobody can. Nobody can program a brain. Nobody can build a brain. Forget about this singularity idea. If you ever heard that, if you never heard, don't worry about it. It's not worth it. If you heard it, discount it. It's not worth it, the paper it was printed in. Basically, the problem here is, how do you get a humanoid robot to move like a human? You need a human or a primate brain. Gordon didn't have one available. None of his students were willing to donate theirs. So we did the next best thing. We got a monkey to walk at Duke University in a treadmill. We recorded the brain activity that underlined that walking, so we showed that we could predict the walking of these monkeys very well, like I showed you with Aurora. And Gordon built a dedicated, very fast internet connection between our lab and his lab at Kyoto. And we basically send these brain signals to CBU1, got CBU1 walking, and video footage describing the walking of CB1 was broadcast back to our monkeys in a big TV screen, so that the monkey walk in the treadmill, seeing these robotic feet and legs walking in Japan. And to get the juice, it was not her movement that got her the juice. It was the correct movement of the robot in Kyoto that got her the orange juice. So as long as the robot was stepping on the ground correctly, the monkeys would get the juice at Duke. Funny enough, this connection around the globe was 20 milliseconds faster than it takes from an electrical brainstorm to leave the monkey's head and reach its leg. So the monkey's foot was touching the ground in Japan 20 milliseconds faster than her foot was touching the ground at Duke. So this is CB1 in one of the late experiments actually walking in Kyoto autonomously under the control of the brain activity of a monkey. It's not, basketball stepping yet, but it's okay. And it can walk. Funny enough, we realized that even when we stopped the treadmill at Duke, if the monkey continued to walk, and Idoia, the monkey that you just saw there, continued to imagine the movements and got the juice as a reward, she didn't need to move either. So she could keep that robot walking just by imagining the trajectories that she had to produce. So this is half of the game. As I told you, half of the game is to get these signals out and to send them to a device that can make a particular motor behavior occur under the control of brain storms. But there's the second half that is as important as the first, because nobody walks without feeling the ground. You need to know where you are. You need to sense the ground, and you need to know where your leg is in space. When you grab something with your hand, it's not enough just to go and throw your hand and grab it. You need to feel how much force you need to apply. Otherwise, you either squish it or you let it slip. So we had to provide tactile feedback to these brains. And we thought that if we had bypassed the body to move, what about if we would bypass the body to send feedback to the brain? Because you have to realize any patient that has a lesion of the spinal cord, below the level of the lesion, it cannot move, as we know, but it cannot sense the body most of the time either. Nothing. It's almost like that part of the body disappeared. But to walk and to do all this stuff, you need to feel your body. So we designed a technique in which tactile information generated by the actuators, in this case a virtual body, would be sent directly to the brain. And these signals went to the part of the brain that we know process touch in normal animals or in human beings. And to test this, we use Avatar, as I mentioned to you. It's like using the video gaming techniques that exist out there. They're well known. We just brought this to the neuroscience laboratory. And we got actually a high school kid to work with our scientists to actually program this thing to work, right? Because most of the students will not know how to do it. And what you will see is the first time that a monkey went in a virtual space using virtual hands to touch objects. Virtual objects, they don't exist, they're virtual. They are visually identical. So when the monkey or you or I look at them, they look like spheres. They're identical. However, each sphere has a microtexture. So when the virtual hand rubs the virtual fingers on the surface, it can sense the microtexture, the tactile properties of that surface, and send this in the form of electrical signals back to the monkey's brain. And to our surprise, without telling anything to these monkeys, just by sending these signals proportional to the texture of these objects, the monkeys learn to interpret the texture of the objects. I'll repeat again. They learn to interpret the texture of objects that are virtual using a virtual hand controlled directly by brain activity. There was no involvement of the body whatsoever. Okay? So this is it. You're going to see a little movie that shows the monkey doing what any of us would do faced with the same task if we had to use our own hands to do it. So there you're going to see monkeys rubbing their virtual fingers on the surface of the object. There are some legends for you, not for the monkeys, because it wouldn't help either, because, as you know, they don't speak English. And there is some sound in the background that was not there for the monkeys either. There was no other cue for the monkeys, just the objects and their virtual hands. The sound in the background is the brain of the monkey firing. So I can hear, you won't probably, but I can hear the neurons firing there. And every time you see a different sound is the message that we are sending back to the brain in the shape of electrical pulses. Okay, we just put this in a loudspeaker so you can hear. And here you have an animal controlling this virtual hand and exploring the surface of the objects. Can you lower it down a little bit? There is only one correct object out of 3. He has to find it by touching, and every time that he finds it, he has to press the center to get the orange juice. And that's what he does. That's the message that we are sending. The animal is thinking, and finally takes a decision. So essentially, we establish a bidirectional dialogue with the brain. It didn't mean anything to you. This sounds like, abstract. But the brain made sense of it. So one type of sound meant very smooth surface. The other sound meant rough. And the third sound meant in between. So there are 3 textures there. And as the correct object was moving position, the animal had to actually identify by touch and then press the center of the object to get the juice. So this is a learning curve over time. This is time. This is the learning. This is what happens when the animal does this with a joystick. It's very quick, and they get to 100% in a couple weeks. So using a joystick to play the same task. Well, that's what happens when they use a virtual hand, and what you just said or saw. It takes 4 weeks, but they get to the same level of proficiency. So they're able to do the task that they would do with their own hands normally. So having done that, the last experiment I want to show you is what is the limit? Where can we go? If we are now dialoguing with the brain, what can we do? We showed you a monkey that can recognize touch, but touch is something that is normal to primates and to us. We all know when I say touch, you know immediately what I'm talking about. Well, we reasoned that we could push the brain a little further. So in these experiments that just got published a couple months ago, we got adult rats, and we tried to see whether we could use the phenomenon that is explaining what is going on here, that is called cortical plasticity, and that is the ability of the brain to reshape itself, to learn new tricks. And we basically tried to see if rats could learn a complete different sensory modality, something that they never experienced in their adult lives. And the idea we had is, could we induce rats to touch otherwise invisible light? Could animals learn to feel, not see, feel light? And what we did was, rats, as you probably know, and mammals, any of us, we cannot see infrared. If you get the clicker of your TV at home and you change the channel or increase the volume, you cannot see the beam that is going to the TV. Neither can rats or any mammal. Snakes can, but mammals cannot. So what we did was to basically put an infrared detector on top of the head of these animals and get the output of these infrared sensors, transform them the same way we did with the monkeys in an electrical language, and deliver this language to the touch cortex, the same part of cortex that I just mentioned to you before with the monkeys. And we asked the questions, can we put these animals in an infrared universe where important things like water, for instance, or source, location of water is coded by infrared beams, and can they learn to identify where they are just by touching this invisible light or perceiving light as a sense of touch? And to our surprise, in about 40 sessions daily, 1 hour a day, living in a universe that is coded in infrared, the rats did. And you're going to see the first one of them. There are many now doing all sorts of crazy things, but this is the first guy, the pioneer rat. It's the Mickey Mouse of neuroscience now. And this is, if you could lower a little bit, because I cannot go lower here. But this rat is in an infrared environment. The only reason you can see anything is because I'm filming this with an infrared camera. And every time a beam of infrared appears, the rat cannot see the light, but he feels the light as a tactile stimulation to its face. And he is able to track the beam, go all the way to the source, and drink the water that comes from underneath. Very quickly, as you can see. And in fact, they develop a complete different behavior. They behave now like bats. They are looking for sound. So they keep moving their heads in the environment in search of the beam of light that none of us could see, nor can hear, but he can feel it. And as he turns the body, the tactile stimulation becomes more intense, more pleasant, and he follows all the way to water. So, again, in 70 sessions, these guys get to 100%, or very close. So they don't miss it anymore. This is an adult brain. So if in Texas there is the Brazilian saying that old dogs don't learn new tricks, forget about it. We all learned, and we learned to the end of our lives. And these animals are totally adults. They are not young rats. And they were capable of assimilating a complete new sensory modality that no mammal has ever experienced before in 4 weeks in North Carolina. So that's not too bad. The amazing part is if you look at the brain of these animals and you measure like we measure continuously for years and years, you can see that these brains, of course, this part of the brain where we put these signals, they're still responding to the skin, to tactile stimulation of the skin. That's what you expect. You're in the touch cortex. But now, these guys are responding to light. It's not supposed to respond to light. In theory, the visual cortex is here. But we made that piece of cortex capable of responding to light. So it's possible that in the future, if someone becomes blind because of a lesion of the occipital pole, you may be able to restore vision by using a different part of the brain to re-put these signals back there. So why I told you all about this new neuroscience, I'm going to finish just by showing you why we want to get. I show you a lot of science, but I want to show you some practical application of this. So you don't think that this is just an abstract exercise. There's much more into it. So soon after we published Aurora's study, we suggested in a Scientific American article that perhaps what we call brain-machine interfaces could become the basis for a new therapy called a neuroprosthetic device, a device that in patients that suffer a lesion of the spinal cord and therefore are paralyzed below the level, what we know now from basic research is that the brain doesn't stop thinking about moving. The brain continues to produce brainstorms related to movements, but the body cannot follow these signals because there is no highway that will take, neuronal highway that will take these signals from the brain to the body. So John Chapin and I suggested in 2000 that what about if we just get these signals out of the head, the way we're doing here, we bypass the lesion, we create a new body, we create a robotic vest, and we make these signals control this robotic vest. That's what got the reviewer to say that we needed professional help. we do need it. It was called funding. That was the professional help. We need it, yeah. Well, we got it. About 6 months ago, in 2009, I created with my friends, Gordon and other friends around the world, it's now 8, 9 countries. This slide is outdated. There's people from Japan, China, all over the world. A non-profit consortium called the Walk Again Project. And being Brazilian, I went to the Brazilian government and said, you're going to have an interesting event in 2014 in the country. It's called the World Cup, the Soccer World Cup. We call football down there because, it's a game played with the feet. That's the reason it's football. I'm still adapting. It's only a quarter of a century that I'm living here. So I went to the Brazilian government and said, Brazil is well known abroad for its football, its beautiful rainforest, sun, music. But that's not the country we want people to know. We want people to think about Brazil as the frontier of science and technology. And the president of Brazil looked at me and said, well, how do we do that? I said, well, there's only one way, doing it. So I proposed to the Brazilian government that we would do the first demonstration of a whole body exoskeleton on the opening ceremony of the Football World Cup. It's about 3 billion people watching, thinking that they were going to see a little more samba, a little more, tropical fruits and exotic dancing. Instead, what the Brazilian government has done is to fund an international consortium that includes all these universities that you saw in the previous slide to build the first exoskeleton, full body exoskeleton controlled by brain activity alone. And what we're going to do is 15 months from now is our moon landing, is our moon shot. We are going to get a Brazilian young adult, 19, 20 years old, paraplegic, to stand in the sideline of this stadium, walk to the midfield, and be in charge of the kickoff of the World Cup. This is... Thank you. This is how Scientific America portrayed this idea. It was elected in August of last year. One of the 10 scientific ideas that, as you say here, is beyond the limits of our science now, but can be done. I told some of the students before, not the whole story, but my grandmother, the one that got me the moon map and got me plotting the Apollo landings all over, used to tell that impossible is only the possible that nobody put enough effort to actually do it. And she raised us like that, believing that if you want to do it, you just need to go and do it, And when we presented this to the Brazilian government, I'm not going to show you the more science. We took with us one of our colleagues in Switzerland is a computer graphics scientist, and he modeled the entire exoskeleton. This is a realistic exoskeleton of a human being inside. This is all realistic. And he played this. He gave it to me so I could play it to the Brazilian president. And that's the idea. That's the nutshell of the idea. It's all wireless. He didn't know that we can do that wireless, but it doesn't matter. The brain signals are going. They'll be responsible for the person to stand up. There are 128 degrees of freedom in this exoskeleton. There's tactile feedback coming from all over to the skin of the neck. And that's what we want to do. So the idea is that this is going to be just another World Cup. But the opening, I hope, is going to be an amazing goal for science. Science for all of humanity. Thank you very much. Thank you.
Thanks, Nicolelis. Thank you so much for that. And we'll be available for questions afterwards. Absolutely fabulous presentation. I must say, before you leave,
sure.
You mentioned the Brazilian World Cup in football. And we understand the difference of football, although the kind we played for the last 20 years doesn't quite measure up to the Brazilian kind. So rather than getting you a Dallas Cowboys cheerleader, we instead got you a proper football jersey.
Oh, thank you.
From the Sim Institute. So
that's wonderful. Thank you. Thank you very much.
Thank you.
Thank you. Thank you. Wonderful.